right? Yeah, so let's have a look into this particular TPDQ of 92 picoseconds and then the TPCQ of 82 picoseconds. And this is kind of characterized from the latch design, and it is nothing to do with the pulse clock generating signals, because once the pulse signal is given to the latch design, the latch output is my Q signal, right? And then P stands for the propagation. So the only thing we have to see is, why is the delay from D to Q higher than the delay from clock to Q? All right. So if in that case, I'll have to look into the latch designs here. So if I consider the latch design here, this is the latch design, a simple CMOS latch design. So I have an inverter here, and then a transmission gate, and then inverter followed by the tri-state inverter. So this inverter and this inverter will ensure that the output noise are not coupled inside the latch. And this particular feedback tri-state inverter helps in ensuring that this particular node is staticized. Right. So let's have a look into this particular design and see that what is the delay from D to Q and what is the delay from C to Q, and then try to understand whether it should be higher. Right. So if this is my the gate level diagram, and so this will be my transistor level diagram. Okay. So let's have a look into it. So what I'm going to do is I'm going to draw the transistor for individual gates here. So I'm going to draw the inverter. So this inverter, so I'm going to draw the transistor here for the inverter, right? So this is my D input, and let me also number it out. So this is transistor PMOS number 1 and NMOS number 2, or rather I'll say the transistor number 1 and transistor number 2. And this is the transmission gate. So I'll just redraw that transmission gates with because it is the transmission gate is anyways has the transistors. So this is phi and this is phi bar. And let me say that this is the node X and then this is the node Y. And let me also write the number as 3 and 4 here. So the NMOS is 3 transistor and the 4th is the PMOS transistor. And then I have this particular inverter. So I'll also draw this particular inverter. So this is VDD and then this is ground. And let's say that this particular transistor is transistor number 5 and 6. And we have this tri-state inverter. So let me draw the tri-state inverter. There should be 4 such inverters. So I'm going to draw it something like this. And ground, and then this is VDD. And this is my Q signal, Q input. And this too will be phi bar and phi here. Remember that this tri-state inverter works when the clock is low here. When the clock is high, we will have this transmission gate to be passing the the signal, and during the phi bar signal, this particular output will be passed from this tri-state inverter. Right. So the phi bar to the NMOS here, and transmission gate will have the phi to the NMOS. And let me also write the transistors here. So we completed phi 6. So I'll write it as 7 and 8, and then finally 9 and 10. So there are 10 transistors, and then so this 10 transistors I have configured into this particular transistor level schematic. But I'm trying to club it in together so that I can visualize what happens to the D to Q output and clock to Q output. Right. So let me map these transistors into that particular transistor schematic, into this particular schematic. So the D signal is going to 1 and 2 transistors, so which are closer to the VDD rail. So this is VDD and then this is ground. Right, so the transistor number 1 is here, the transistor number 2 is here, that is where the input D is going. Right, transistor is closer to the VDD and then the ground rail. So that is good. So this is done. And then we have the 3 and 4. So 3 goes to the so this is 3 and then this is 4. Right, on one side it is the X input, on one side it is the X input, on one side it is the X input for both the 3 and 4 transistors, and the other diffusion is the Y node. So the other diffusion is Y node here, and that's why I have connected this X and Y together. So my 3 and 4 transistors are also done. All right. And now I'm taking this particular transistor 5 and 5 bar signal. So that is basically 9 and 10, 9 on the PMOS side. So the transistor number 9 and then the transistor number 10 with an gate signal as 5 and 5 bar respectively, 9 and 10 transistors. Right. On one side it is the Y input. So this Y input is there. Or rather, you know, this output is nothing but the Y output. So that's what it is. So I should have written it before. So this is the output, is the Y output. Right. So for the 9 and 10 transistors, so the 9 and 10 transistors, on one side it is the Y output. So this is the Y output, the 9 and 10 transistors. All right. And on the other diffusion, it goes and gets connected to the 7 and 8 transistors. Right. So the 9 transistors, on one side diffusion it is Y, and on the other side it goes to this particular inverter, and I'm going to call this as let's say 7 and 8. Right. And then 7 and 8, look at the 7 and 8, it is nothing but it is going to the rail on one side and then the rail on the other side of the 8 transistor. So it is it satisfies 8 and 7 VDD, and 8 gets connected to the ground. The input to the 7 and 8 is nothing but the Q signal, and the input to the 7 and 8 is the Q signal here. And finally, so this particular inverter also output is Q, the input is Y here. Right, so this output Q gets is the output of the 5, 6 transistor. So I'm going to write it as transistor number 5 and 6, where the input is Y and the output is Q. Right, so I've covered all the 10 transistors here and try to make it as compact as possible. So this transmission gate, especially this transmission gate, and especially some part of this tri-state inverter, we are trying to club it in, right? Club it in this particular stage. Right, having the same the nodes X, Y, and then it takes this particular transistor, or rather this particular clocks, that the clock signals are given appropriately. Right, so in that sense, this schematic is very, very similar to this particular gate level diagram, or it satisfies the gate level diagram. And now if I actually find out the diffusion common or the merged diffusion capacitances here, it is nothing but I have written it as this one and this one, 1 and 4 transistor will have a merged diffusion capacitance of C1. Y is nothing but the node of the merged diffusion node of the 9 and 4 transistor, which is C2, and similarly we will have C22 and C11 on the pull down side. Now if I look into this particular 4 capacitances, then we should be able to make a comment on the delay from D to Q or the delay from the clock to Q. Now let's say that if the D arrives earlier than the clock, so the D signal is given here, so the D arrives earlier than the clock, so the clock arrives later, right? So this 4 transistors, we have the clock signals, and let's say that the clock arrives later, but the D arrives earlier. So if the D arrives earlier, we know that C1 as well as C11 can either get discharged completely, or it will be charged completely. And whenever the clock arrives, then the output before the clock leaving the TP, C1 and C11 will either be discharged or charged before the clock, leaving the propagation clock to Q determined by the charging of only C2 and C22. Right, so what it means is if the D signal arrives earlier, then the C1 and C11 is either discharged or charged, it has already been done. And then when the clock arrives, it leaves only this particular capacitance C2 and C22 to be charged appropriately. Right. So the delay here from clock to Q actually depends on only the C2 and C22 capacitance to be either charged or discharged. And it doesn't, the C1 and C11 are not in the picture at all, because it is already been charged or it is already been discharged. Right, but if let's say if it's the other case, if the D arrives later, here, then the clock, although the clock is has arrived earlier, right? Even though if it has done that way, the C2 charge will be shared by the C1, right? It will be only be shared by the C1, but it doesn't go to VDD or go to the ground. Right, it will be only be shared by C2 will share with the C1, C22 will share with C11, and then vice versa. So if the D arrives later, then it provides a path of the VDD, a source path of VDD or a sink path of ground. And that is when all the charge that has been there in C2, C1, C22 and C11 will either be discharged completely to the ground or it will be charged to the VDD. Right? So when the D arrives later than the clock, then all the capacitors will be either be charged or discharged, and hence for the delay from D to Q, we have to account for all the capacitances here. Whereas for determining the clock to Q, right, determining the clock to Q, only C2 and C22 transistors are accountable. Right, C1 and C11 has anyways been completely discharged or it has been charged completely. All right, so that is why we always get the TPDQ to be slightly higher than the TPCQ for both the pulse latches as well as in the latch design. So that's something it's the characteristics of the latch, and it's not the characteristics of the clock or the pulse signal. Right? Hope you are able to understand this.